Hello, we start with 5.1. This is about proving identities. We're going to learn in this section how to prove trig identities. So they will give you an identity and try to prove it. To do so, let's go over some guidelines. If we are asked to prove, for example, let's say A equals B. The way to prove identities, either we take A and work it out and get to B, so we don't touch B at all, we don't work with B. B is just the final answer in the back of the book. Or we can go from B and get to A. So in this case, A is the answer in the back of the book. What are some of the guidelines to approach trig identities? First, you always go from the larger side to the smaller one because you will have more options to deal with or to use. If we have fractions, we combine them. If we can use factoring, do so. Factoring or expanding. These are some of the guidelines. If in case you get to the point that you can rationalize by multiplying by the conjugate, top and bottom, do so. And the last thing is you can always convert things into sine and cosine using the basic trig identities that we will recall in a minute. Another good thing to know from algebra that is being applied in trig is the factoring, especially x squared minus y squared, the difference of two squares. That's an x minus y times x plus y. And the other one, x to the fourth minus y to the fourth. This factors as x squared minus y squared times x squared plus y squared. But again, x squared minus y squared, we just factored as x minus y, x plus y. And we keep the other one the same. So what are the basic trig identities that we learned before already? Those will be tools for us to help us prove more complicated identities in today's lesson. The basic identities that we start with, the first one, the reciprocal identities. The tangent theta is 1 over cotan theta. Secant theta, 1 over cosine theta. Cosecant theta is 1 over sine. Those are the reciprocal identities. We know the ratios. Tangent theta, sine over cosine, and cotan theta, cosine over sine. And we have the Pythagorean identities, the sine squared theta plus cosine squared theta equals 1. Keep in mind, from this we can get a lot of things that we can solve for sine squared. And we can solve for cosine squared. Also, from the sine squared plus cosine squared, we can come up with two identities. One is 1 plus tangent squared theta is secant squared, and the other one, 1 plus cotan squared theta is cosecant squared. Those can be found or can be derived by deriving this Pythagorean identity by first time by sine squared and the next time by cosine squared. It will give us these two other identities. These are all the basic identities that we need to know to prove more complicated identities. Let's look at an example. Say we are asked to prove tangent theta over secant theta equals sine theta. Notice the larger side is the left side, so I start with this side, so I'm gonna rewrite it first. I cannot combine fractions, I can't factor, I can't expand, so the only thing I have to do is, and I keep an eye on the right hand side, which is sine, so that motivates me to convert things into sine and cosine. So tangent is sine theta over cosine theta. Secant is 1 over cosine theta. Keep in mind that's the division sign. If we have a over b divided by c over d, you can write it a over b times d over c. So the division becomes multiplication. So I'm gonna keep the top the same, top fraction, switch division to multiplication, and flip the other fraction. Notice how cosecant cancel, and that gives us what we need. Let's look at more difficult one. Cotan x plus 1 equals cosine x times cosecant x plus secant x. Well, let's start with the right hand side, so I'm going to write that down. And let's keep this the same. I can't do anything with cosine for now, but cosecant is 1 over sine, and secant is 1 over cosine. Then if you see, the left hand side has no parentheses, so we're gonna distribute this by this and this by this. So when you multiply cosine by 1 over sine, it goes on the top. Same thing, cosine x over cosine x. What's cosine over sine? That's cotangent, and cosine over cosine is 1, and that's what the left hand side is. So that proves the identity. More examples. Let's say cosecant square x minus 1, cosecant square x minus cosecant x equals 1 plus sine x. I would start with the left hand side, as we got more options to deal with. I'm gonna rewrite it first, and then what we can do with this is I can factor the top one, cosecant x minus 1, cosecant x plus 1, and we can factor cosecant x in the denominator. So these cancel out, so that gives me cosecant x plus 1 over cosecant x. If you look at the right hand side, there's no cosecant, it's only sine x in there. So what we need to do here is convert this into sine. We know cosecant by the reciprocal identities, 1 over sine. The 1 stays the same over 1, and this is 1 over sine. This is called complex fraction. The easiest way to simplify complex fractions is to multiply by the least common denominator. Least common denominator, all these fractions, this, and this, is simply sine x. So it's sine x. So I'm going to multiply the top of each one by sine x. Sine x. Sine x. That will clean up the fractions. Let's see what we get. The sine cancel out. That gives me 1 plus sine x. And the denominator is 1. And that's simply 1 plus sine x. And that's what we needed. Let's look at another example. Sine to the 4t minus cosine to the 4t over sine squared t cosine squared t. So the left hand side that I'm gonna start with gives me more options to work with here. Let's see what we can do. We can factor the top using the algebra stuff here. the x to the fourth minus y to the fourth. Same thing, but it's being applied to trig in this case. So we get sine squared t minus cosine squared t times sine squared t plus cosine squared t. Keep the denominator the same. Now we know sine squared plus cosine squared, this is 1. So I'm only having on the top sine squared t minus cosine squared t over sine squared t cosine squared t. Now I'm gonna go back, look, I need secant square minus cosecant square. So I see something minus something. So what we can do, we can use this algebraic property that says you can split this like so. A over c minus b over c. So here we can do this sine squared t over sine squared t cosine squared t minus cosine squared t over sine squared t cosine squared t. And then what we get here, these cancel out, so that gives us 1 over cosine square. These cancel out, 1 over sine square. But wait, what's 1 over cosine? It's secant, so it's secant square. 1 over sine is cosecant square. That's why the basic identities are very important, and that's what we needed to prove. More examples. What about if we are asked to prove 1 over 1 minus sine x plus 1 minus sine x over cosine square x equals 2 secant square x. Of course, we start with the left hand side. And there's so many ways to work with the left hand side. I'm rewriting first. One thing I'm thinking about, convert the cosine square into 1 minus sine square. That's one way to do it. Or if you'd like to just do combine, because we have fractions, we combine them. The LCD is 1 minus sine x times cosine square x, basically the product of these two denominators. So now what we need on the here, I have 1 minus sine, I'm missing cosine square, so I multiply top and bottom by cosine square. Here I have cosine square, I need to multiply by 1 minus sine x. 1 minus sine x. Then on the top we get cosine square x plus, distribute this one, 1 times 1, 1, 1 times sine x, sine times 1 sine, and negative by negative positive sine square x. Let's see what we get. The sine square plus cosine square is 1, plus another 1, that's a 2, minus 2 copies of sine x. And let's keep this the same. Why am I keeping this the same? Remember, the answer has to be 2 secant square. So to get to that point, cosecant is 1 over cosine. So I want to keep that cosine square in the denominator as is. I don't want to distribute that for now. So what I'm going to do is, on the top I can factor the 2 out. That will give me 1 minus sine x. Keep this the same, and cosine square the same. See, the 1 minus sine cancel, so that gives 2 over cosine square x. Now we go backwards, 2 secant square x, and that's what we were looking for. So proving identities is the matter of practice. The more examples you do, the better. Let's look at a slightly different kind of example, how we prove 1 plus sine alpha, or let's make it cosine here, over sine equals sine alpha over 1 minus cosine alpha. The thing about this, we can do factoring, we can do combine the fractions, we can convert into sine cosine because everything is in terms of sine and cosine. So let's go back to the guidelines. So we've seen some examples about, most of the question went from the larger side to the smaller side. We combined fractions in one of the examples. We did some factoring. We convert into sine and cosine, but we haven't rationalized yet. So what about trying to rationalize? Use over this last example here. So let's start with the left hand side. To rationalize this, we're gonna multiply top and bottom by either 1 minus cosine or by sine. So anything is fine. So let's multiply by sine, the same as the denominator. Notice on the right hand side I have a sine. So when I multiply the tops, I just keep it written in this form. Rewrite it like so. Do not distribute because I do need the sign, so I want to save the sign here, and then I can do whatever I want in the denominator. Sine times sine in the denominator is sine squared. But keep an eye on the right hand side, the one that I'm trying to prove. It says I need 1 minus cosine. Well, how am I going to get 1 minus cosine? Let's keep this the same for now. I need to write sine squared in terms of cosine. So we know it's 1 minus cosine squared from the identity again, the Pythagorean identity. So sine squared is 1 minus cosine squared. That's where that came from. Now what can I do in the denominator? I can factor the denominator. This looks like 1 square minus cosine square. So it looks like x squared minus y squared, which factors into x minus y, x plus y. And that's what I'm going to do. 1 plus cosine alpha, 1 minus cosine alpha. So these cancel out. And that gives us sine alpha over 1 minus cosine alpha. And that's what we were looking for. See, sine alpha over 1 minus cosine alpha. So again, the more examples you do, the easier those identities become. I can show one more example. 1 minus cosine to the 4th alpha over 1 plus cosine squared alpha equals sine squared alpha. Of course, you can pause the video and try it. First, it's important to try the problem. So to start with this, I'm going to take the larger side, which is the left hand side, and get to the right hand side. What do I do with this? Well, one thing I can do in the top, that looks like 1 to the 4th minus cosine to the 4th. Again, this factors as x squared minus y squared, x squared plus y squared. So I'm going to use it here. 1 squared minus cosine squared alpha, 1 squared plus cosine squared alpha. Keep the denominator the same. Notice how this is going to cancel out to this. That will leave 1 minus cosine squared alpha. Is that what they ask us to prove? Oh no, sine squared. But we do know that 1 minus cosine squared alpha from the Pythagorean identity here is sine squared. So this can be replaced with sine squared alpha. And that gives us what we need.